One. Welcome everyone to Zoom for Thought, edition 2 of 2021. This week we're going to have Sam Spiro talking to us about some selected picks from Extremal Combinatorics.
Thank you. Yes, and that was perfect pronunciation, Baki. Yeah, so we're talking about Extremal Combinatorics today. And the first question we want to answer is, what the heck is Extremal Combinatorics anyway? So the best way to answer this is by the kinds of problems you solve in Extremal Combinatorics. And very broadly speaking, these are problems of the flavor where we want to figure out how large a certain parameter of a certain set of combinatorial objects can be. So one example of this is Ramsey theory, which Emily talked about last week. So the central problem kind of is to talk about, to figure out how large of a clique Kn one can find before every two coloring of its edges contains a monochromatic clique of size t. Here, the parameter we're kind of maximizing over is the number of vertices here. So because there's a maximum in the problem statement, this is more or less an Extremal Combinatorics problem. You might complain that it's technically not in this format here, but you can reparameterize things to say that the parameter you're doing is number of vertices, and the set of combinatorial objects you're considering are two colored cliques which don't contain a monochromatic clique of size. There's a bit of a winding there, but I assure you it's of this form. And in Extremal Combinatorics, it's often the case that we don't. All right, yeah. So there will maybe some lag. Okay.
I think I'm not getting a lag.
Yeah, this was happening with us too with Abacus. If you want, we could stop the recording and I can send the slides to everyone. So if there is lag, they can follow along.
Yeah, we might as well do that. I'm gonna pause the recording. So 3, 2, 1, and we're back.
All right. Yeah. So let me just restart the slide. I don't know where we're before, but right. So in Extremal Combinatorics, it's often too much to ask for exact answers to a problem. So for example, there's no hope or expectation that we could ever find the exact Ramsey number of the clique of size 1,000 or whatever. So instead, what we often try and do is get effective balance on our problem. We settle for that, but we can get, we will sometimes get exact answers, but we'll often settle for approximation. Because of this, we often end up using tools from analysis in order to obtain our desired bounds. And this talk will mostly not be about how to apply these methods, but I'll briefly summarize some of them. So probably the most cited result is the Cauchy-Schwarz inequality, which says that the square of the sum of products of two sequences of real numbers is at most the product of the sum of the squares.
I might inject that we have often discussed ways to figure out if someone is a combinatorialist or a probabilist. So I can tell you that if you square the left-hand side of Cauchy-Schwarz instead of take a square root on the other side, then you're a combinatorialist. And if you're an analyst, you do the square root on the right-hand side.
Ironically, when I first wrote this, I had it the other way, but it was harder for me to say out loud, so I had to swap them. So
you are an analyst. All right.
Yeah.
Moving on. Sorry about that.
Yeah. No. Thank you. Thank you for the important interjection. Yeah. So in addition to Cauchy-Schwarz, we also use some other inequalities like the arithmetic mean and geometric mean inequality, or just the AMGM inequality. Says that the geometric mean, which is the product of your terms to the 1 over nth power, is at most the arithmetic mean, which you can also think of as the expected value of this if you're randomly picking a thing. And it's not just explicit bounds that or inequalities that we cite. We also use a lot of like thinking from analysis. So like one common technique is to split your problem up into dyadic intervals in some way. So for example, you might consider a graph theory problem, and one way to approach it would be to split your vertices into those which have degrees between 2 to the k-1 and 2 to the k, and then solve your problem within each of these sets, and then put everything back together to get some. Yeah, so this is broadly speaking a lot of the approach, but now we want to talk about some specific examples of results and problems in Extremal Combinatorics. And so there are many more. Yeah. Okay. So the first thing I want to talk about is a specific subarea of extremal graph theory, and the main thing we'll be considering is F-free graphs. So given two graphs F and G, we say that the graph G is F-free if it contains no copy of F as a subgraph. So one example of this is if we look at the complete bipartite graph, KST, which has parts of size S and T, and we look at a triangle, then the complete bipartite graph is triangle free. And we'll do this by proof by picture. So one way is you have this K24 and a triangle here, and you just say, oh, do we have a triangle? Well, you could say, oh, do these two edges form a triangle? No, because we're missing an edge here. Do these two edges form a triangle? No, because we're missing this edge here. And you can check all these cases. This is not going to be a triangle, and it's not too difficult to actually rigorously prove that none of these complete bipartite graphs actually is not. So this brings us to kind of the fundamental problem in extremal graph theory, at least the one that I'm interested in, which is how many edges can an n-vertex F-free graph have? So again, this is the same language in our general problem. Our parameter that we're trying to maximize over is the number of edges, and our category of graphs is n-vertex F-free graph. And I'll denote this quantity, the maximum number of edges, by x and f, and we'll call this either the extremal number or the Turon number of the graph f. So let me pause and ask if there's any questions about the definition of either f-free or the extremal number, because we'll be using this for like 80% of the talk. So if you have questions about this definition, now is the time to say something. Okay, cool. Right, so again, x and f is the maximum number of edges in n-vertex F-free graph. And one easy example to prove is a lower bound on this quantity for the triangle of roughly n squared over 4. And to prove this, we make the following observation. Take G to be the complete bipartite graph with parts of sizes roughly n over 2 each, in such a way that you get an n-vertex graph. This is triangle free by what we said before. All complete bipartite graphs are triangle free. And moreover, it has n squared over 4 edges because the number of edges is just is a general ST if you have a KST, because you just have all the number of ways to pick a vertex here and all the number of ways to pick a vertex down there. In any case, we've exhibited now a graph which has n vertices, is triangle free, and which has n squared over 4 edges. So by definition of the extremal number being the maximum over all such graphs, we get this lower. And a famous result of Mantel says that this is the best you can do. The maximum number of edges in an n-vertex triangle free graph is n squared over 4. And moreover, the unique graph which achieves this bound is the complete balanced bipartite graph. This is kind of the foundational result in at least this area of extremal graph theory. And you can generalize it considerably, namely to cliques. So KT will denote the T vertex clique. So this is the graph on T vertices, such that every two vertices are adjacent to each other. And it was proven by Turon that this extremal number is exactly this quantity here. And the construction is a generalization of Mantel's construction. So for Mantel, we had we split our graph into 2 parts of roughly equal sizes and added all the edges between them. That's a complete balanced bipartite graph. And for cliques of size T, we split the graph into T-1 clunks, and then of roughly the same size, and add all the edges between them. One can check that it has this construction has this many edges, and that it also is clique free. So his result really is in proving that this is best possible. Yeah, so there was a bit of a gap between Mantel proving this in 1907 and Turon, who proved this basically the second result in extremal graph theory. So he was really the one who recognized that, like, oh, it's actually interesting to do this in kind of a general setting. And Turon's theorem itself can be generalized quite considerably. And to state this generalization, I want to recall what the chromatic number of a graph G is. So this is the fewest number of colors needed to properly color the vertex set of a graph G. And by a proper coloring, I mean that every pair of adjacent vertices receives a distinct color. So let me again define this by definition, or by picture. Yeah, defining by definition, I guess, would be rather trivial. Anyway, here's a 3 coloring of the Peterson graph. So each vertex is given either red, blue, or green color. And it's a proper coloring because if you look at any edge, you'll see that there are 2 different colors on both ends. This shows that the chromatic number of the Peterson graph is at most 3. And it's not too hard to show that if you try and do this with 2 colors, you'll end up getting a monochromatic edge, one where both endpoints are the same color. So the chromatic number of the Peterson graph is in fact exactly 3. So now that we know what the chromatic number of the graph is, we can state the Erdős-Stone theorem, which I've heard described as the fundamental theorem in extremal graph theory. And this says that for any graph f, the extremal number of this is asymptotic, or basically asymptotic, to this quantity here, plus some small error term. If you're not familiar with asymptotic notation, you can just basically pretend this is a small error term. And this almost generalizes Tron's theorem. So Tron's theorem, if you look at F, the clique on T vertices, its chromatic number is T. And this part here is exactly the quantity you get in Tron's number minus this error term here. But the real power of Ayers-Stone is that it works for any graph F with at least one edge, I should say. So for example, if we ask what the extremal number is of the Pearson graph, this immediately tells us that asymptotically, the maximum number of edges in a Pearson graph free graph is roughly half n choose 2, which is half the edges. And certainly a priori, who knows what the best way to avoid this thing is in an arbitrary n vertex graph. It's a weird looking thing, but the Ayers-Stone theorem like immediately gives it to us once we know the chromatic number. And again, I won't talk about the proof, but I'll just say a few words on this. The lower bound is very easy. You can take the again, it's like complete balance by T part chi of F minus 1 partite graph, just like in Tron's theorem, and that works as a lower bound. And the upper bound is significantly harder. It's not super hard, but it's definitely non-trivial. And I'll note that while this gives the best, almost an exact, or it gives an asymptotic result, an exact asymptotic result for any graph F, it only works to get the exact result. You need chi of F here to be at least 3. If the chromatic number of F is 2, then this term here ends up canceling, and you're only left with this expression here, which just says that the extremal number is of a lower order of magnitude than n squared. And the problem of figuring this function out when F is bipartite, or equivalently when chi of F equals 2, is a very difficult problem. And even for many simple families of graphs, we don't know what the right answer is. So let me briefly summarize some results when F is bipartite. So first of all, it's a relatively easy exercise to prove that if F is a tree on K vertices, that is, if it's a connected graph with no cycle, then its extremal number is at most this quantity here. And it's a famous conjecture of Ayers and Schoch that you can do better by a factor of 2 for every tree, and we can just divide this quantity by 2. And some comments on this is that a lower bound of this form is easy to prove. You can just take a disjoint union of cliques of size k minus 1. This won't contain a tree because it has to be all in one clique, and we're assuming we have k vertices. It's also, the upper bound is known to be true for simple graphs or simple families of graphs like paths and trees and these sorts of things. But overall, the conjecture is still open. Another nice class of bipartite graphs is the complete graphs, KST. And Kovar, Schoch, and Tron have a relatively easy proof that the order of magnitude of this extremal number is the most n to the 2 minus 1 over s. So here I've adopted the somewhat non-standard notation, less than. If you're familiar with asymptotic notation, this is just equivalent to saying equals big O of the quantity. If you don't know what that means, you can just pretend this is a less than or equal to, and it'll basically be correct. And it's conjectured that this upper bound here is correct in terms of order of magnitude, that this extremal number should be the order n to the 2 minus 1. And this is known to be true in a couple of cases. Namely, so here we have, again, 2 parts, S and T, where S is the smaller part. And it's if T is much larger than the smaller part S, then it is known to be true, namely if T is larger than S minus 1 factorial. And this is because it's known that there exist graphs called projective norm graphs. And these graphs have this many edges and avoid this quantity here. And this norm here is not the analysis norm, sadly, Baki. It's so the algebraic number theoretic kind of definition of a norm. So basically, you consider some construction involving finite fields and like some elementary algebraic number theory, which I won't get into details because I barely understand them myself. But it's not that hard. I understood it at one point in my life. And another natural class of bipartite graphs is even cycles. So it was proven by Erdish, or Erdish claimed to have a proof, and then Bonish and Monovitz were the ones to formally write down one, showing that the extremal number is at most this quantity in order of magnitude. And as the same for complete bipartite graphs, it's conjectured that the order of magnitude here is exactly what the upfront here. They'll note that there's a bit of thinking that this may not always be the case. So this is a little more contested, but in any case, it is known to be true in a couple of cases, namely when k equals 2, 3, or 5, due to some graphs coming from something called generalized polygons. Interestingly, it's not known to be true for k equals 4. So in other words, for 4 cycles, 6 cycles, and 10 cycles, we know what the extremal number is. But for 8 cycles, we don't, which is kind of weird. And yeah, it's a very strange phenomenon. And one point that I want to kind of emphasize here is that it is often the case, for example, for complete bipartite graphs and even cycles, that it's relatively easy to get a reasonable upper bound, which we often think is correct. But to actually get the correct lower bound, it requires some construction of a graph. And these graphs are often highly symmetric and weird in some way, and they use tools from algebra, geometry, and number theory. Yeah, any questions about what I've talked about at this point before we change gears slightly? Okay, cool. So next I want to talk about some generalization of graphs. And there are many different ways to do this. So probably a lot of you are familiar with directed graphs, multigraphs, and these are all fine generalizations, and each of them have their own sorts of extremal problems that you can ask. But the main generalization that I'm interested in is hypergraphs. So a hypergraph is best seen by this picture, but formally it's a pair V and E, where V is a set of vertices and E is a set of edges, where an edge is a subset of the vertex set. So pictorially, we often denote such hypergraphs as follows. So here, your vertex set is these 6 points here. And your edge set is represented by these ellipses. So if you have an edge that contains, say, these 3 vertices, we draw it by this circle here. We have another edge containing these 3 vertices, which we represent by this ellipse here, and another edge containing these 3 vertices, which we represent by this ellipse here. An important case is when all the edges have the same size, which is what exactly happens here, for example, in which case we say the hypergraph is R uniform if all the edges have size R. In particular, a 2 uniform hypergraph is just a graph. So formally speaking, a graph is a set of vertices together with some collection of pairs of vertices called edges, which we represent by just putting dots and then adding lines whenever there's an edge. So a hypergraph is just the same, but now instead of having edges be pairs of vertices, they're now arbitrary subsets of vertices. And if we're uniform, the sets are all the same size. Any questions on about the definition of a hypergraph before I go on and do a bunch of things with hypergraphs? Okay, cool. And if at any point you get lost, just think of hypergraphs as graphs, and you'll be mostly fine. Okay, so we can ask the exact same problem, the question we had before. So namely, if F is an R uniform hypergraph, we define X and F to be the maximum number of edges in n vertex R uniform hypergraph H, which does not contain F as a subgraph. So when R equals 2, this is exactly the graph drawn problem, because now we're looking at 2 uniform hypergraphs, which again are just graphs. And very little is known about these extremal numbers. I would say probably even less than what we know for bipartite graphs. In particular, we don't know asymptotically the extremal number of this thing here, which is kind of formally defined here, but in words, what this thing is it's the simplest non-trivial peak that is not a graph. So if you recall, Turon's theorem, which is kind of the second theorem in this theory, gives you the exact extremal number for graph peaks. But if we step up to 3 uniform hypergraphs, even the simplest case, we don't know asymptotically what the value is. So it's much, much harder to think for hypergraphs. I'll note that we have a conjecture for what this the exact Turon number should be, and we have pretty good asymptotics bounds, but we don't have the exact thing. And part of the heuristic reason why this is hard is for graph leaks, there was a unique graph which achieved this maximum value. But for hypergraphs, it's known that if our conjectured value is correct, there are many, many constructions which achieve this thing here, which makes proving an upper bound significantly harder. And in general, many of the problems which are used for graphs become much harder for hypergraphs, in part because things which used to be true for graphs or which are strongly conjectured to be true for graphs no longer hold. For example, there being many, many constructions for such a relatively simple hypergraph. And one particular result which I want to highlight is the following. So a relatively simple hypergraph is the matching M2R. So this is just the hypergraph, which is just two disjoint sets of size R. So here I've depicted M23. And we want to, again, ask about M2R-free hypergraphs. And the observation is that any such hypergraph is intersecting, meaning that if you look at two edges in such a hypergraph, they have to, because they don't look like this, they have to intersect in at least one vertex. Because if they're disjoint, then H in particular contains two disjoint edges, which we're trying to have not happen. And one construction which has this intersecting property is SVR, which is the hypergraph where we take all the edges which contain some given vertex V. In particular, because every edge contains this vertex V, you can't have this picture here where they're disjoint because V is in one of these. You're implicitly assuming V is in one of these, but we know it's in both. And just as a very concrete example, if we look at the graph version of this, we take a vertex V and then add every edge involving this vertex, which just puts it out like this, and that's just the star graph. And in general, we'll call this hypergraph SVR a star. And a very famous theorem of Erdős-Cohen-Bratto proves that if n is sufficiently large, then the extremal number of this 2 matching is this quantity here. And moreover, the unique construction will be the star hypergraph that we mentioned before. And there's one kind of natural generalization of this EKR theorem, which is now, instead of looking at two disjoint edges, you can ask, well, what happens with S distinct edges? And it's another famous conjecture of Erdős called the Erdős matching conjecture, which says that when n is sufficiently large, the extremal number is one of these 2 quantities here. And I won't go through the details of why this is a reasonable thing to think about, but I'll note that if you go through the details, you can check that this is a special case of this theorem when S equals 2. Any questions at this point before we change gears once again? And as I know before, this talk will be relatively short, so again, do feel free to all right, now we'll go to our last main topic, which is combinatorial number theory. And the main object we're interested in here is k-term arithmetic progressions, or simply KAPs. And these are sets of integers of the form a plus d, a plus 2d, and so on. So each element just increases by some common difference, d. And here, the central question is to ask how many integers in 1 up to n can a set A have if it does not contain any k-term arithmetic progression. And for the purpose of this talk, I'll adopt the very non-standard notation, xnkap, which is the size of the largest k-term arithmetic progression, which lies in the subset of first n positive integers. And there are some pretty good results for this problem. So first is a result of Behrend, which proves that for k greater than or equal to 3, there exists a set of integers which does not contain a k-term arithmetic progression, which is relatively large. It's small decaying factor times n, which is the best you could possibly afford. And Ferretti, or not, sorry, Samoretti, for all these Hungarians, ending in Eddie. It's very, very difficult. So it helps, I guess, anyway. Anyway, right, so Samoretti proved that this decaying factor is necessary to some extent. So in particular for all k, he proved that the extremal number here is little of n. So it's smaller order of magnitude of n, or in words, every dense set of integers contains arbitrary long arithmetic progressions. So I'll note that the bounds in Semireti's theorem are atrocious. They are good. It's a very strong theorem, but the actual little onus here is very weak. And you could ask to get stronger quantitative bounds, and in particular in the simplest non-trivial case, which is 3-term arithmetic progressions. I'll note that the original upper bound or non-trivial upper bound for this extremal number was first proven by Roth. And more generally, in this case, there are much stronger quantitative bounds, which are. So the most recent results that I could find was by Schoen, who proved this in May of last year, which, ignoring these extra log terms, is basically n divided by log n for the size of a set, which does not contain an 3-term arithmetic progression. And just getting things on the same plane, if you ignore these terms here, this upper bound is roughly of the form e to the minus log n. And the best lower bound is still of the form that Barron proved, namely e to the minus roughly square root of log n times n, though this constant has been improved by Elkins. And it's a very big problem in combinatorial number theory to get to really close this gap for 3-term arithmetic progressions. Yeah, so any questions here, because this is the last of the important mathematical content of the talk. Okay, so one extra little thing I wanted to mention is Erdős numbers. So as you might have noticed from this talk is that Erdős has done a lot of things. So both in extremal combinatorics and number theory and analysis and all sorts of jazz. So he's written a lot of papers and with a lot of people. And because of this, people have come up with this kind of amusing statistic of the Erdős number. So Paul Erdős is said to have Erdős number 0. And if you write a paper with someone who has Erdős number k, then you get Erdős number k plus 1, or both k plus 1. So for example, if you've written a paper with Erdős, you have Erdős number 1. If you haven't written a paper with Erdős, but you've written a paper with one of his co-authors, you get Erdős number 2, and so on. And almost every professional mathematician has a relatively small Erdős number. Namely, I don't think I've ever seen one that isn't in the single digits. Maybe if you go back to like Gauss, maybe he has Erdős number bigger than 10, but that's quite saying a lot. So for example, I was just playing around with UCSD professors and trying to find someone with a large Erdős number, and the largest I found, though it didn't look too hard, is Klaus Sorensen, who's the number theorist. So he wrote a paper with this person, who wrote a paper with this person, who wrote a paper with this person, who wrote a paper with Erdős. So he has Erdős number 4. But if you start looking in extremal combinatorics people, you'll often get much smaller Erdős numbers. So for example, I, not to brag, wrote a paper with Van Chung, who wrote a paper with Paul Erdős, so my Erdős number is 2. And this is basically the best one can hope for these days, because Erdős passed away in the 90s, so he's not writing too many papers these days. But there have been some posthumous papers written by him. So I think sometime in like 2010 or so, Steve Butler got an Erdős number 1, despite I don't think ever having met Erdős. So it's still possible, but in general, 2 is the best one can hope for. Okay. So up to this point, we've discussed a lot of results and problems in extremal combinatorics. And I just wanted to, before we leave, briefly recall some of these results and kind of a hip and easy to remember way to do it. So do it as follows. Bear in mind for this RAP, I've got a bear in mind and no KAP. You won't be progressing when I'm the MC. Got enough fat dishes for a PhD. When we spar, you'll be breathless and you can see PR. Seeing stars when I hit you with that EKR. Am I getting my point across? Should I spell it out for you? AMGM, all your products are less than my average, mu. Was that too intense? Were you only semi-ready? You're acting so dense I can fly semi-ready. I'm not the kind of person you should turn on. Got edge to the max like I'm turn on. I'm an extremal guy. Erdős honed. My level's so high, it's like I'm Erdős stone. Getting 10 out of 10. Fall, winter, spring, and summer. Your only 10 is your Erdős number. Now, I'd rather be nice, stay home and count. But if you want to fight, you're going down for the count. Bring your whole clique, I'll bring my acrobatics. Color you black and blue until you're monochromatic. So keep coming and coming, there's no need for dramatics. I'll keep cutting and cutting and chop you into dyadics. Don't think I'm carefree just because I'm doing mathematics. If you mess with me, things get hypergraphic. And that's all, folks.
Let us thank the speaker. Oh man, that was worth the wait.
And before we go to general questions, let me just answer the first couple ones that I know all of you have right now. So yes, I did make the wrap first and then design the talk around explaining it. In particular, the only reason I shoehorned that slide in about the connection with analysis and combinatorics or whatever is because I needed to introduce the AMGM inequality and dyadic intervals. The second thing is, yes, I am open to performing at weddings and or bar and bat mitzvahs. My tentative wrapper name is Lil O. And the very last thing I'll mention is that I wasn't even planning this, but let's see, how can I switch? But the talk ended up having 99 slides. So you could say that I've got 99 slides, but a Birch ain't one, which I can't switch to right now because of the way it's over. But Brian Birch is a number theorist whose work is unrelated to anything that's going on here. So that's why he does not appear. But with that, if there are any real questions and or comments, I'm happy to hear them. Also, I can't see the chat for whatever reason. So if anyone said anything important there, feel free to let me know.
I have a massively naive shot in the dark.
Yeah.
I'm always confused when there are these very innocent looking conjectures that are like impossible. I was wondering if there's any connection at all to like homotopy groups of spheres or something.
Yeah, not that I'm aware of. There are some hypergraph problems. So like you can triangulate a sphere, right? And this defines a hypergraph where you have like the triangles are edges and your points are the vertex set. And you could ask, how many edges can you have in a hypergraph which avoids any triangulation of a sphere or a torus or any other manifold? And these are questions that have been like looked into, and there is some results. I don't know of any connection from there to homotopy theory, but I wouldn't be shocked if there was.
Sweet. Okay. Tom notes that Daniel Litt has an MO post about this.
Okay.
Good stuff. All right. Any other questions or comments? All right. Let us thank the speaker once more. All right. I'm going to stop recording.